Welcome to this session. This session, we are going to prove some properties of determinants and evaluate determinants using the properties we stated earlier in the first session. So copy the equation. So let's start giving solutions. So problem 1. So solution. So we have 0, a b squared, a c squared, a squared b, 0, bc squared, and then a squared c, cb squared, and then 0. Now, let's go step by step. Considering the first column, you see a squared is a common factor. So this is the same as writing a squared determinant of 0, b, c, and then these others remain the way they are. Remember, the assumption we are taking here is that you have watched the first video on properties of determinants. So when we have a scalar multiplying up a whole column of a determinant, we can simply factor out that scalar out of the determinant and find the determinant of the resulting matrix. Now, when you go to the second column, you see also b squared is common. So we factor out b squared, so it'll be a squared b squared, determinant of 0, b, c, a, 0, c. Now we keep this one. Now, when we go to the third column, we see c is a common factor to all these elements. So we factor out, so a squared, b squared, c squared, determinant of 0, b, c, a, 0, c. Now this will give us a, b, 0. So we have just, up to that point, we have just playing with factorization of a scalar that is common to columns. Now, the next step, we say, let's have our column 1 to be column 1, and then column 2 to be column 2 minus column 3. So we'll have, this will be a squared, b squared, c squared determinant of, and then column 3 remains to be column 3. 0, b, c. Now this minus this is 0. This minus this is minus b. This minus this is c. Then a, b, 0. So that's what we have. Now, because we have 0, 0, then it is easier to use compact expansion along the first row, so that we'll have this determinant to be a squared, b squared, c squared, and then a determinant of bc minus bc. So this will give us now a power 3, b squared, c squared. This will be bc plus bc. And this gives us a cubed b squared c squared times 2bc, whose solution will be 2a cubed, b cubed, and c cubed. So that is the solution to that problem. Number 2, we were to show that determinant of x, y, z, x squared, y squared, z squared, x cubed, y cubed, z cubed is given by x, y, z into x minus y into y minus z into z minus x. So proof. So I have this determinant x, y, z, x squared, y squared, z squared, x cubed, y cubed, z cubed. I'll say let column 1 be column 1 minus column 2, and let column 2 be column 2 minus column 3, and let's skip column 3. Or even before doing that, by the way, we can simplify before even going to columns, considering the first column. You see a common factor here is x. So we can say you factor out x, and then you'll have 1 x, x squared. These others remain the way they are. That's what we have. Now, when you check the second column, also y is a common factor. So you factor out y. So you have xy, 1 x, x squared, 1 y, y squared, and then keep these others. Now also, third column, z is common, so factor out z. So we'll have x, y, z. Determinant 1 x, x squared, 1 y, y squared, 1 z, z squared. Next, you say, now let column 1 be column 1 minus column 2. Let column 2 be column 2 minus column 3. Let column 3. Okay, let's do step by step so that we don't mix several steps. So let's deal with column 1 first. And let's give this one column 2. Let's give this one column 3. So this will give us x, y, z. So 1 minus 2 is 0, x minus y, x squared minus y squared, and then 1, y, y squared, 1, z, z squared. And then next one, we say let column 1 remains to be column 1, column 2 now to be column 2 minus column 3, and let column 3 remains to be column 3. So this leads us to x, y, z, determinant of 0, x minus y, x squared minus y squared. So this will be 0, y minus z, y squared minus z squared. This is 1, z, z squared. And you see now, because we have 2 zeros in the first row, we use compact expansion to find the determinant. This sign is plus, minus, plus. So this will be x, y, z times 1, determinant x minus y, y minus z, x squared minus y squared, y squared minus z squared. And you see this will be x, y, z, x minus y, y squared minus z squared, minus y minus z into x squared minus y squared. And this will be x, y, z into x minus y. These are difference of 2 squares, so x minus z, y minus z, and then y plus z. Here we have minus y minus z. This also a difference of 2 squares, so x minus y and x plus y, then close brackets. So you see x minus y, y minus z is common factor here. So you can say x, y, z into x minus y, y minus z into here we'll have y plus z, and here we have minus x plus y. So which will be x, y, z into x minus y, y minus z into y plus z minus x minus y. And you see this and this cancels out. So we'll have x, y, z, x minus y, y minus z, and then z minus x. So that result is proved. X, y, z, x minus y, y minus z, z minus x. Thank you.